very happy to be here. I think the last time I had the honor of presenting on the screen was some 5 years ago in my PhD defense, and it always feels like home, especially now that there's a carpet here. I'm going to have you bear with me in this presentation because it's a deep dive in a bit of a different topic than that one we've seen before. So the relationship between that might be quite a lot in the pixels, let's say, in how this works, in what the pixel wants to be and what we want the pixel to be, and you'll see why those pixels come back every single time throughout the work. Because of NITS. So I entitled my talk "Digital Materials Across Scales" because I do want indeed to have this kind of view on how we deal with material both at the global scale and at the local scale, and how we can create this kind of link or this kind of dialogue between the large scale and the zoomed-in scale. More specifically, if I think of those in terms of geometry, we could categorize those into, so one, the global geometry type of scale, where we think of architectural geometry or structurally informed geometry, and this comes very much from the heritage of having been here and in the BRG, as some might think I still am. They are not mutually exclusive, and sometimes they are actually, they work quite well together. But it's not only always about the global geometry, where we talk about these units, but actually also having a little bit of a deep dive in local geometry. And that local geometry could very well be understood in terms of material geometry, so specifically where we place that material within a structure, and having those tailored material properties. So really being able to say, I would like there to be this type of material here, and I would like it to perform this way, or vice versa if the material wants to do that. What these types of approaches, both at those kind of double scales, can allow us maybe is look into this reduction of raw material use, reuse, functionality, and architectural expression generally, so that we can go across all of those scales. And if we really, if we keep that on the one side, what I'm really trying to do most of the time is couple the way we design, build, and usually that's very specific, and fabricate, so that it can enable us to achieve these goals. And those enablers are actually computational tools. I put fabrication very specifically in between designing and constructing, or designing and building, because most of the work that I do is linked to fabrication, so I would like it to be there explicitly. And I don't talk maybe as explicitly about design, but you'll see how that gets informed through these. To get quite to the point in the deep dive, that's in that sense, I really work on how we could do better with the materials that we have, so that we use less materials. In the PhD that was developed within this building, actually, I looked at how we could build complex concrete structures in a more effective way, because if we have these kind of concrete structures that are thin, filigree, span large spaces, have doubly curved geometries, and so on, as you might see in this image. We can reduce that material use, but what we usually have is a problem in how we build them. And this image is by no means an actual is in any way a sort of criticism to the master builders, Felix Candela or Pierre-Luigi Nervi. It's actually kind of an homage to say that these people at that time were also looking into this, into material efficiency and how we might rationalize geometry and build that and come up with systems to build. So if anything, it's looking at that, taking inspiration from that, and trying to translate that to the modern day. In that context, the system that I usually talk about is a lightweight formwork system made with knitted textiles very specifically. Now, textiles are used for formwork more often, and they have been kind of explored throughout the past 100 years or so. What's special about what I do is the knitting side of things in that sense. The reasoning behind that is that they're fast to produce. They can allow us to reduce this waste and be used with minimal intrusion. So I'll give you a few examples of that throughout the presentation. The idea behind it is that somehow if we move away from a traditional formwork system, so one that we're used to where you have timber forms or milled EPS forms or whatnot, into one that uses a membrane as a forming system, we have an avenue to use less material, both in the structure and in the building thereof. There are really, how something like this works is we start with a design, hopefully a structurally informed design, so one that uses less material. For that design, you produce a fitting textile, a fitting knitted textile using existing machines. So it's a robot of a different sort. That textile is then taken to site and it's tensioned into a rig. And that tensioning can be done in any number of ways. So you could do this with an exterior frame, as you see here, with cables, with splines, with inflatables, however you see fit, or however the structure deems fit. And then it's coated with a thin coating that gives it an initial rigidity to make the formwork. Now this step so far is quite important because for all of their advantages, knitted textiles are very soft. So if you were to attempt casting anything into them, they'll deform quite drastically. And that doesn't really bode well with us wanting to get the structure that we want to get out of it. So keep that in mind a little bit. There are two challenges in this. The first challenge is if we do have a design, how do we get to the fabricated textile for it? And those can be addressed through computational pipelines. And the second challenge is, if we do have that textile somehow magically fabricated, and it's not so magical actually, you'll see, how do we use it to construct things, to build things? And actually, throughout the examples that I'm giving you today, I'd like to show those two processes. Starting first with the construction side of things, very briefly, very fast. The first time we tested this out was, on the knitting and at the large scale, was during the Knit Candela project in 2018. You'll see that we give these names to projects because they're very much homages to the famous shell builders in question. So in this case, Felix Candela, where we reinterpreted that geometry of the high bars into one that is fully doubly curved and explored how that concrete structure could be built using a textile. What you'll see in I'm not going into details about it because it just shows, it's a project that I've shown a couple of times, and I hope it is one to show how the system works. So then that kind of textile that gets manufactured is tensioned in a rig. It's coated with a cement paste coating in this case on the one side, and then concrete is applied rather traditionally in a manual way, as you can see in that image. And you end up at the end of it, when the concrete hardens, you can take away the frame. And you end up with a structure that looks a little bit like this, that kind of has this, this play between the hard concrete exterior and the soft textile interior. And that's just a video of it in those sense. Why this project is particularly important, or a pivotal point, is because it looks at the construction of the concrete side of things, right? So how we can have such a lightweight system carry a heavy concrete load, or whatever other molding material you might want to mold. And on the other hand, because it actually really looks at how we might scale those textiles and have them very specific for the purpose that we need. And some of the takeaways from that are that, well, the textile themselves, the formwork, the 50 square meters, including cables that were needed, but excluding the outer frame, cost about 2,500 euros, 2,500 francs, 2,500 US dollars in the meantime, well, whatever translates. They weighed about 25 kilos, and the cable net weighed another 30, so in the end, 55 kilos carried 5 tons of concrete. And here is where it gets really interesting, at least for now, is that it took 36 hours of machining time to produce those 50 square meters of doubly curved surfaces, and it would usually take about 750 hours to mill 50 square meters of a comparable doubly curved surface. And it took 14 weeks from design to the structure standing there. And that bodes something, that says something about the kind of activity that can be achieved if we have the types of systems that enable that. Now, this is a little bit cheeky because, of course, the 14 weeks doesn't take into account the 2 years of development for these kind of things beforehand, but once you have it, it will take you 14 weeks, possibly. But what are those developments that enable this? So what makes this possible, actually, is the fabrication pipeline side of things, so the first one that I showed you in the image. And that fabrication pipeline is important because usually, though it may seem trivial, these types of machines are usually used for clothes, so for the human scale. And they work with a set of instructions that very much looks like a bitmap. And that's where the pixels come in. So those are the pixels that I promised you in the beginning, and they will keep coming back. But those pixels tell the machine how to work, where to place the material, and their different colors also tell you what type of operation should be done at that particular spot. So it's actually encoding a type of action into a very simple 2D pixel grid in that sense, and that brings out 3D geometry with all sorts of features in the end, if done correctly. Most of the time, these types of things, these types of images or instructions are made by highly skilled technicians that know exactly where to place which feature or which operation so that you would get the geometry or the feature that you want in the end. And that is very laborious because you have to imagine that each one of those pixels represents a square in reality of about 2 by 5 millimeters, sometimes less, sometimes more. But it's a very small resolution to work with if you really need to click it by hand. Now, if we want to do this at a larger scale, what we need is these kind of computational pipelines that translate that design into an instruction for the machine automatically. And that's what enabled this kind of project or the 2 years of development beforehand. What this really does is actually a 3D remeshing, or looking at a 3D remeshing of the object or the geometry that we want into a topology that can then be represented as a 2D grid. And that 2D grid can be represented as a pixel grid that can be then given to the machine. So there's this direct relationship between a 3D object and a 2D representation of that object. Meaning that you actually produce something 2D that is 3D. That's what the machine looks like in general. It's kind of just a plotter that just goes line by line and adds material where you've told it to add material in that sense. I'm showing it because it's not, these types of developments are not only interesting for us, but they're interesting for machine manufacturers as well, specifically because it gives them an into a different field or a different sector that they're not actually active in. So it's nice when you also make other manufacturers happy. Most of the time, it's not only about making them happy, but though we show these kind of machines in isolation, because in a research context, it's usually just one, the truth is that there are many machines like this all over the world. So there are hundreds in factories churning away socks or whatever else they're doing for us. So if we can actually make those types of instructions, we can really send them very lightly wherever and have things be produced locally very easily. So we can really tap into this type of power of production that already exists there. The next project that I wanted to show you was one that we finished in 2022. It started out as just an ETH project, then I moved to Delft and it turned into a cross-country collaboration in that sense. But let's say it's an evolution of the first one that really looks again into the formwork system itself, but not only that, into how we might bring it closer to what something that industry might understand as implementable a little bit sooner than the other. In this case, as the name suggests, it was called Knit Nervi, and it is inspired by Pierluigi Nervi and the Palazzetto dello Sport. So the pavilion was built at the Maxi Museum in Rome, so just a couple of 100 meters down the street from this. And what you'll see here is this kind of diagrid of ribs, so a ribbed shell structure, that is also maybe not as easy to build always. So we look into how this might be built. You'll see that kind of interpretation of this geometry in the funnel shell that you see here. And because, of course, we had Lotte working on it. Lotte is a PhD student still at the BRG, but comes from Stuttgart. So you might see this nice little droplet that's evocative of these kind of Frei Otto geometries as well. What you'll see here in the geometries that we try to make this kind of diagrid structure, you'll see that it looks a little bit more recognizable probably to industry, and it includes reinforcement. This is what it looks like from above in the end, so you'll see the kind of diagrid. It looks small, mostly because in any photo that we take, it's either dwarfed by the museum, that is huge, or it seems somewhere placed alone in space. The truth is, for context, this is about 2 times the size of the previous structure I showed you. So this is 9 meters in diameter and 120 square meters of textile, right? So we have I'm going to come back to this, but we have an order of magnitude of scale in that sense. So this type of process also started with a form-finding exercise in the beginning, right, to get to the geometry of the shell. So you'll see how this is reinterpreted by moving the supports up and down. And in this case, what we also wanted to do is make sure that there is even less, let's say, waste or support structure that's not used subsequently. So in this case, we took the rebars that would be the rebars in concrete. They're a bending active grid shell, and they would become part of the structure, but they are the ones in this case supporting the textile with some 3D printed nodes from it. This is what it looks like during construction, just so it gives you a little bit of an idea of how that bending active grid shell looks like as a structure on its own, and how this gets covered with the textile in the end that would become the formwork for concrete. So if we explode those kind of geometries, it looks a little bit like this. There's some standard scaffolding support, and that's the only part that's not used within the structure eventually, but the standard scaffolding support can be taken away and used anywhere else. So there's really very little waste there. There's the grid shell falsework that becomes reinforcement within the structure if it were to be cast, the knitted shuttering, and what would have been the ribbed concrete shell that results from it. Now, full disclosure, if it wasn't clear from the images already, we did not cast this. There are 2 reasons for that. And while you see how the first part was being built up in rather traditional ways, the reason for not casting that was, for one thing, we did it before, so we could reasonably assume that we've shown that you can use it, although you never do until you do. Secondly, it was a temporary exhibition, so if we were going to make a point about being sustainable about concrete use and then make a structure for 5 months and demolish it, we thought maybe the message is not completely there. But third of all, it was in a museum, and the visitors to the museum were not necessarily people from the construction sector or architecture, so it gave us an opportunity to look at how we might offer the visitors an X-ray through the structure or an understanding of what a structure is built up like in general terms. And think of it think of the whole build-up in a fully deconstructible way, so that it's modular and could be constructed and deconstructed instead of torn down. What we did is we built first the grid shell. So you'll see it ends up looking like this. We measured everything about it, and then decided to start the production of the textile after the grid shell was built, so that you would create an actual tailored fitting textile for it. I'm bringing back this image because in this case, why that's again an enabler is because instead of, as in a normal process, starting to produce all of the components for the building at the same time, because otherwise you wouldn't have time to deliver it, we could stagger it, so we could wait, get extra information, and start the production of the textile later. But also because it did require a further development of these kind of pipelines. Now we're talking about 120 square meters, not a 50, so we're looking into a little bit of a different scale in terms of computing power or how you generate these patterns. And we also started looking into how we might address very specific material properties locally. So if we start looking, in this case, until now I've been talking about the global geometry of it, but in this project, local geometry starts playing a role in the same way through a real specific tailored materiality locally. So what you'll see is in the transparencies, and this will come, they're a little bit difficult to photograph, but In the transparent parts in between the diagrid, you'll see that there's a little bit of a gradient for each one of, so you'll have graded material properties there that are fully controlled during fabrication, but they're also fully controlled during that generation process. And to do this means that you need to generate your patterns or your pixels in a very precise manner, otherwise it becomes a lot more difficult to control. So in terms of computational pipelines, that meant a development. In this case, we didn't have just 4 pieces as in the previous one, but actually 72 pieces that needed to be made, so you need to generate quite a lot of data and make sure that you can control that. Just to give you a quick idea of it, we started with a density distribution for how we wanted the material to be. The diagrid themselves doesn't have a density variation because that represents the concrete. And then for each one of those pieces, what it would do is generate that 3D topology, right, of points that represents a 2D grid. In this case, just for context, it's about 30,000 generated points to get to one of these. Each one of those understands its relationship to the structure in space, understands what it's supposed to be as a function in the final one. So for example, the magenta bits know that they need to be a channel, and then the other ones know that they need to have a particular density. Now, the 2D representation of it would look something like this, but there's another catch. This type of grid would only mean that each one of those pixels is actually a 4x4 grid, so it needs a post-processing part where you can transform those into actual instructions for the machine. So they've been generated actually on a 4x4 grid instead of very specifically on a 2mm by 2mm grid. That looks a little bit like this. I just go really quickly through it, but it's this kind of post-processing of a pixel into extra pixels that really decide these types of functionality that come within the final product. And then after all of the different steps are there, what you'll get is an image that looks a little bit like this that can actually be fed to the machine to create all of those different densities within the final geometry. You'll see again the machine producing these kind of textiles. You'll see all of the pieces, and the classical, we've put it in one bag and took it to site because it's lightweight and easy to take there. But again, we could just send the instructions. And then this time around, you'll see that you don't need necessarily a qualified team of builders to put things up, but a rather unskilled worker that can just assemble these things in sometimes a little bit more time than they thought. So this is what it ended up looking like in the end. A few views from the inside, and here I think it's a little bit more clear how you can see these kind of transparencies or graded material properties that can be done with such pipelines. Again, that kind of project looks at both the efficient deployable flexible formworks on the one hand, but also at graded material properties and the computational fabrication pipelines that are needed for it. So it's really across different topics at different scales. Now, if we started with 50 square meters and the second project ended up with 120 square meters, it turns out that, I mean, this was 2018, this is 2022. It turns out that roughly every 2 to 3 years, I like to double the amount of textile that we make, and I like to pretend that I'm a construction worker. So this year, we doubled that yet again. So we went to 300 square meters of textile and being construction workers, because we built a pavilion for Bruges, for the Bruges Triennale. It's called Common Thread. We've done this together with Soil and Summum Engineering. And it was built in, this time around it has nothing to do with concrete or things like this. It's purely looking into how we can apply these techniques and how we can scale them up in a few ways. For the Triennale, the Triennale theme is spaces of possibilities, and actually what they're looking at is, because Bruges is kind of seen as an open-air museum, is looking at spaces that are not usually visited and are not accessed, and how we might bring in new life or new use into these spaces. So actually, it's very difficult to see on here, but it's just within it's a structure within a large courtyard that is actually otherwise never really used, but beautiful. It's inconspicuous, so you get there through a garage door that you may or may not find, and it might just give you this kind of wormhole idea and tell you, hey, come in. And if you do, you go through this kind of down the rabbit hole in this simple sort of tunnel, but that flips you inside out in moments and creates this kind of space and this, within the courtyard to try to thread, let's say, a sort of connection between outside and inside, and between the past and the future. And why I'm saying between the past and the future is because actually what Bruges is also known for is something that is also rather computational in a physical way. But Bruges is known for lace making, so there's a lot of lace making there. So the inspiration there was into using a textile, was into looking into these kind of lace making techniques and how those translate in the same way to our machines, and how we make this type of, well, let's call it digital lace in this case, and how we could transform those techniques. So in this case, again, there's a point of trying to work on those computational tools, this time because I need to get the kind of very specific control over these types of lace that we designed. Actually, everything needed to be generated at a 2x2 pixel grid instead of a 4x4, and so on. So it just gets bigger and bigger in terms of computational needs in that sense. What you'll see is that it's quite, after production, it's quite easy to put up. I mean, it's basically a tent, a lightweight tent that we've put up there. It took about 10 days to put together, so this time lapse really makes it look a bit too easy. It wasn't quite that easy, but we like to make things look easy, and it's a little bit, it looks a little bit like this in the end. It is a very tall structure, so it did challenge both the geometry of things, but mostly in how we create those textiles in the end. And finally, one of the images that I really like is because, to some extent, of course, from the part that is here in looking into the past and cathedrals, this is my textile cathedral instead of a stone cathedral as they usually are. Finally, I have, because I did call it digital materials across scale, and we kept going high, up and up in terms of scale. The truth is we don't always need to go up and up. So I hope that in 3 years I'm not going to be on a scaffold doing the 1,000 square meter pavilion, but rather, or somebody else might be, and I just design it, that's fine. I'm trying to go back down in scale so that we can understand some of these mechanisms a lot better. One of the projects that the last bigger project that I wanted to show is one that was born out of having been children of this building. So it was done together with Katrin and Norman, so with TU Braunschweig and TU Munich. And it's actually looking into both an educational side of things, but also in because we did it together with students, but it's actually taking a concept that from each one of us and scaling that up a little bit. So it started with a small bridge that you can see at the end of the corridor here. And we said, hey, let's scale that up and see how we can automate some of these processes. So the textile is not very special. And if anything, compared to all of the other projects, it's the one that went the wrongest of them because of the smaller scale, I guess. And combine that with automated fabrication technologies that are being developed at the other universities as well. So in this case, instead of having a manual concreting process, there's a automated path planning and robotic fabrication setup to add that first coating and to add all of the other layers on top of it. So it's really trying to solve different parts of the problem in terms of construction and digitalization at different moments in time and at different scales or in different contexts in that sense. So if I were to sum that up, what I'm trying to get at is looking at the structure as a whole, right, at deployable formworks, at graded materials on the other hand, so mitigating these kind of two scales, and how we might have adaptive or hybrid systems, so the different types of materials or models that we can put in there, and how we can address that automated fabrication of it. There are a few hinges in this. First, the computational design one that I've kind of put forward everywhere, so how we design both of those scales. Then how we have those computational fabrication pipelines, so we can get to that automated fabrication at whatever scale it is or for whichever part of the structure. But the more interesting one that at the moment that's really pushing me into the smaller scale or into the pixel scale is that, well, while we might be able to design these materials and we might be able to very specifically fabricate them and control their fabrication, one piece of the puzzle that is missing is that doesn't necessarily mean we know how they behave and we know how to make sure that they have the behavior that we want. So one of the very large missing links here is the predictive material properties, so figuring out how those are, and that would be what allows us to close that fabrication design loop. And in that sense, I'm moving always close now into the more zoomed in scale. And I wanted to just give you very brief examples that are newer work that move into the scale is looking at the different types of textures of the material and the local architectures, how they combine and what kind of an influence they have. So really zooming into the material. How they deform or how they perform, how different combinations of those materials do perform, and how we might be able to start understanding their performance in that sense. In these cases, what you'll see is that we don't have a coating, but we're trying to understand how this works really with the deformation of loads in that sense, and how we might start thinking of these in modular terms. I'm working with a textile, meaning it's flexible. Now, we try to freeze that flexibility with a coating, but what if we were not to freeze that flexibility? That means that we might have an opportunity for reconfiguration, reuse, and modularity within it, because you could get different geometries from the same piece, and you can get different behaviors from the same kind of material grading within. So that's really difficult to understand at the moment, and that's something that pushes me to go there. So there are just some examples of recent work in that sense. So what you'll see here is also this kind of reuse of the same piece over and over again. I'll skip over the other ones because it kind of ties into a structural reuse part of things and how we might map, let's say, a existing domain where we've had a structure into a target domain, the structure that we want to build. So we're exploring these things also with concrete and with wind blade turbines. So it's really this kind of mapping of two spaces onto each other, regardless of your source or your target space. And at the very, very last, I want to highlight the people that have made my life really, really nice for the past 3 years and have absolutely helped me get there with what I've been showing you. So there's a team of wonderful students and PhD students in Delft, where we work on 3 different topics, basically. A lot of it is the simulation, prediction, and design that I've shown you, but we also look at structural reuse and adaptive and hybrid deployable systems. So although it might not be immediately clear where all of the AI or machine learning comes in, it's in the pixels, I promise you. So thank you very much.
We're ready for questions, if anybody has them.
Yeah, so this is maybe just more technical, but as far as I understand, it's flexible in a way, but also you have to be super prepared, right? You think in millimeters. So when it comes then to building the structure, it could happen that it's maybe too short. Like as far as I understand, with the bridge, there was a problem. So, but is it inflexible? Can you adapt? Because if you are then on the building side, you cannot change anything for this framework anymore, right?
That's a very good question. So the flexibility is both a challenge and an opportunity. So on the one hand, because it's flexible, well, I'll address the size thing first. First of all, yes, just like with the bridge, we need a calibration step. So you need to make sure that your algorithms produce the things but that's relatively simple. You calibrate, you do something, you test it out, you calibrate it, you'll get you'll get there. What I'd like to do is bypass the calibration, and that's where some of these developments on predicting material properties or having those material models help. But let's say that's something that can be taken care of. The flexibility that remains is that you go to site and you'll have something that can move because it's flexible, right? It's not rigid, so I'll span it, and if I step on it, it's going to deform, and it's very difficult to control how this deforms and so on. So that brings a huge challenge with it. On the other hand, it's adaptable. So as opposed to something that's very rigid, and if you get to site and it doesn't fit, it won't fit no matter what you do, there's some room for fitting it in this case. So you could adapt to the site, you could adapt to slightly different support conditions. Stretching it more or less, you stretch it more in one direction, it might stretch a little bit less in the other, so it really depends. But it doesn't need to be millimeter precise in that sense. If you're, I'd want it to be, but that's something else.
I was wondering, what is your take on the industry of construction when it comes to bringing this to an application beyond a temporary pavilion? Because I think when it comes to concrete, you bring to the table nervi, etc. Certain things, when you look at them, you know they were built in a time where code allowed for that. Nowadays, codes have a different maturity and different requirements, and a lot of what we look into in terms of concrete use and the energy they take, the amount of money, a lot of it is really pinned around the issue of what is required for somebody to build by code.
Sure.
Meaning, and that is one of the major obstacles for certain things that are really into fabrication to truly enter the world of construction in a larger scope with a true impact, I think, beyond the research. So I was wondering what's your take on that? Because I feel like if there is a place like ETH where those possibilities can happen, I think this is a good platform where I think the policies of bringing research into the real world have at least a possibility. I'm wondering what is your take on the timeline in which certain things could come to fruition?
That's a very good question. So, and it's very true. One that I get more often nowadays, because I'm in the civil engineering department, they're like, oh, what does the Eurocode say? And the Eurocode doesn't say much about this particular. But the truth is that, so on the one hand, I don't necessarily concern myself with it in the sense that what I'm proposing is a means to get to a structure, and it's usually the structure that needs to abide by the code. So if you can design the structure that abides by the code, then you will be fine. But you're right. The structures that I mentioned are, of course, thinner, less reinforced, and so on and so forth. So the codes might be a little bit different. But I don't think that the problem there might be a paradigm shift or a shift in our thinking about how what the structure in the end needs to be. So that's one of the things. I do less work on that, to be honest. But I think there's plenty of possibility there. Usually, it does mean that there needs to be some extra testing that needs to be done just to prove that. So as far as I know, in Switzerland at least, or in Germany, or in most places, these kind of things can be done through testing as well. The formwork itself doesn't change that. It just enables it. It just enables you to create a different type of structure.
Yeah, specific testing to prove that it works, the structure, and testing every single element of a building would allow you to pass code, and that's also why the reason which this thing is done there for real.
Sure.
It's a no-go, and I was wondering if there is a place where certain anomalies, like this one, that produce a certain level of saving, which is really what you're advocating. We're saving using this system. Is there a way in which this could truly enter the reality of building without having to go through that? Like if the code will become intelligent enough, if AI will become intelligent enough to actually bypass all those testing that make this impossible.
That would be the dream, right?
Yeah.
But no, that would be the dream. But
Maybe the AI is not really just about the pixel. I think there is something to make this
that's a very good comment.
truly effective, which is a macro problem, which I think when they ask me about these issues as an engineer, like, I actually think policy is one of the major issues.
Absolutely.
To be changed, not really our research as architects. But anyway.
I think both, and probably the research pushes that policy to be changed as well. So it's a double one. I'll be honest. I don't work on the policy side of things, right? So that's not that's. I think it's very important. Yes. If I can have an answer to that, we recently got a European project, and there is a construction company that's involved in it. They are very interested in making it work. They think it's very feasible to make it work. So if you can get a construction company that's usually very to say yes, then you're already a step closer, because they will push for it. And if they want to implement it, they will push for that change somewhere, or they'll look for the avenues as well. So for me, the indication that there is room for it is actually in somebody like that joining a project, to be honest. But yes, you're right. Lots needs to be done on that.
I had a question.
Yes.
And it's more on the sense of how these projects are conceived. Are they, like, I understand that there are projects that are part of a class, so you have students developing the tools, and then you eventually
No, they're
test.
not.
They're not. So that's what I wanted to, because we were here at ETH, and some of the pavilions were a class group. So I wanted to know, how did you come up with the projects? What's your, like, if every of the projects that you show us had a different path, so you have like a firm, or you have an industry partner, or then you have motivation, or you have something to, like, how did they come to be in your repertoire or your portfolio? And how, like, are these collaborative projects? Are they belonging to a class, or this is, like, I would like just to understand.
Yeah, sure.
To give the,
So generally, they're not part of a class. The only one that had an educational component very specifically is the bridge part, and that was meant as a, let's put our technologies together and let's look at it also from an educational point of view. The other ones weren't. They were opportunities somehow. So the first one was the first two, let's be honest, are opportunities at museums that came to BRG. So that's the way. And then they are all very collaborative. None of these things can be. I hope that also the kind of the credits are there. So there are usually big teams behind them that look at all of the different aspects of it, right? So Nit Candela and Nit Nervi were that. The Triennale, I was approached by an architect. So Soil is a New York-based company. They got commissioned by the Triennale to do a installation for the Triennale that deals with the public space. So it's really an architectural intervention, and they wanted to do it with a textile, and they ended up on my doorstep, and it ended up being a collaborative project where we looked at how this could be done with a knitted structure and a tensile structure and so on. So that one was one of the smallest teams, actually. We were just one or two people from the architect, 2 people on our side, so me and a research assistant, 3 people in the engineering team. So they're all different, but mostly they were not educational projects, actually.
because I wanted to write my idea of what
Yeah.
Elena was saying about how do you actually make this into code, and I think a way to make it into code is just to spread the word and have as many people as possible touching it, seeing it work. And I think this also relates to the idea of is it coming from an industry, is it coming from whom? So then this really makes a change. If it's coming from you, then you can challenge some code. Like this could really be something like a proof of concept that then can really share and be shared.
To be quite honest, I mean, all of these things take time, right? So it's not an excuse, but in the beginning you start with, can this even work? So you're trying to make it work. You try to show that these things kind of work. Till you get to the code, Yeah, I mean, and now we're getting to the code. So I guess having the discussion of the code is quite nice because it means that at least there's a conviction that, oh, it could work. So now how could we actually make it work, right?
Maybe I can ask a quick question as well. So, big fan.
Thank you.
I really enjoy I really appreciate the fact that you tap into this kind of these industrial processes and even the machines. So it's not some kind of artisanal practice, but it taps into infrastructures that we have available to us already. So this is fantastic. And then yeah, also how these structures come about. I mean, lightness would be the word I would choose, right? But I'm curious about a few things that you didn't talk about. So I'm curious about the figures that these pavilions have. I'm curious about the shape that they acquire. So is it always the flaunting of the means of their production that produces these shapes? Or does it come from elsewhere? Does it drop from the sky, or does it come?
It doesn't. It doesn't drop from the sky, but it is a bit contrived, right? So it's, or maybe it's not contrived, but it's always a dialogue between, sure, the global inspiration, right? Which with the Felix Candela and the Pierluigi Nervi comes quite a lot from a rationalization of form and that efficiency and shells and so on. So you look into this and to coming close to compression only. So you take inspiration, those kind of principles. In the last one, it's not so much about that as it is. There are only particular, as it was about. Yes, there's a particular way to work with a textile. It's a tensile system, so you'll have to abide by the rules of a tensile system to get to these geometries. You cannot just do whatever else. So it's always a dialogue of including the principles of what kind of shapes this type of technique can take and what kind of shapes you want to achieve in particular ways. So it's never in a void, because quite honestly, with the usual going about things of saying, I came up with this idea and now we're going to make it with this and then we pass it along, it will never work. So it's always actually a continuous dialogue between those two, and they inform each other, right? So you start with, okay, we have a tensile system, so that informs the types of geometries that we might get, but at the same time we bring other things that inform those geometries and constrain this further. So it's usually this kind of dialogue.
Thank you. Actually, maybe following up on that question, I'm curious because, of course, working with textiles primarily, right? The geometry is informed by that technique. What is your experience, at least in terms of maybe struggling with or trying to incorporate other types of materials? So, like the first project, of course, is concrete, that's formwork, but the project with Soil is fiberglass rods.
Yep, that's correct.
Right, and so besides fiberglass, what are other possibilities that you may have thought about, entertaining, even wanted to try?
Well, some of the easy ones are we've included rebars, or we've included inflatables, so you can use some of those. Something that I haven't shown, but shape memory alloys. That can be used in that. They're not, but that moves a little bit away, and you might have seen it. That moves a little bit away, maybe from the concrete formwork side of things, right? And it goes into functional integration somewhere else. I'm using basalt fiber as well, and we use it as a formwork for glass, for example, in a different project that I didn't show. So technical fibers, but also not so technical fibers. Natural ones, specifically for growth in some situations, but it's really just a dance of putting together flexible with rigid elements. And actually, the last one is it's quite difficult because of the fiber glass rod with they're actually two flexible elements, so the complexities of things kind of compound there. So I usually try to take some of the complexity out somewhere. I don't know if that answers it, but a few different things.
Yeah, I think it's really interesting because there's always this sort of, let's say, tension between wanting
Tension
to,
is the right word, yes.
Well, yeah, pun not intended. Tension between trying to do everything with one material versus, when you start to incorporate more different layers and systems, and it goes back to the code kind of question is, at what point or how much do we need to ask of the single material, but then how can we connect it to the other systems that are necessary for it?
But that is very true. I don't believe in single materials, and I don't believe in holy grails, so I don't think that this is the holy grail of everything that should be applied to absolutely anything at any time. It's more of an appropriate tool for the appropriate moment in that sense.
Any other questions? No.
As a follow-up, well, first of all, thank you for the presentation. I love all the explorations. I want to start from the precedent you shared with us, Pierluigi Narvis-Palazzetto, that tells the story of negotiation between material as a premium and cheap labor to make an optimized structure. And looking at the sequence of projects you showed us, you kind of see instances where there's like more. Some projects are, like one project was more material kind of intensive, another one was more labor intensive, and the other one was maybe somewhere in between, at least that was my understanding. So my question is, do you see like direction or like your research converge into a sweet spot where you have like a controlled or intentional like amount of all these components? Because like thinking about there's a lot of machinery involved, so that might have an effect on cost. There's more labor.
I don't think there's a single equilibrium, if that's what you're asking. I think it's very much site dependent, project dependent, and let's call it brief dependent in that sense, and locality. So what you can get. So no, I don't believe that there will be a sort of, and the recipe is this no matter where you apply it. The other constraints will be there, and they will inform this, right? So it will be a sort of, okay, well, in this context, as it has been throughout history and as it has been for Nervi's work or anybody else's work, right? It says, suddenly material is expensive, but labor is cheap, so we can do this and we don't need to do that. Or suddenly material is super cheap and labor is expensive, so you kind of invert those. So I think it will have a lot to do. I think all of those components might have a sweet spot themselves, but then depending on where and for what purpose it's used, it will have a different balance of the different components. Just
Thank you so much for the lecture. It makes the whole concrete framework so easy. It looks like. I just wanted to ask, did you ever explain why you chose blue?
What was? Well, it is one of those things that I think is just going to stick with me from now on. It's going to be blue, and that's my signature color. But it wasn't something that was that is intentional. Well, it is intentional, but it wasn't something that intentional. So for the first one, for Niscandela, it just we wanted the colors. It was a nice backdrop. It was just. And it was a little bit of an inspiration of a Jaisco dress that has a lot of these different colors. The second one around, I particularly love that type of blue, so I wanted that. But it kind of got informed by the museum in the sense that the space is so gray or white or concrete that anything you put there needs to be a little bit of a pop of color, but then you don't want it to be red or something of the sort. And there was a fountain in front of it, and the name of the artist escapes me, but he's famous, that had a blue, and we said, why don't we just echo that? So it came to be. I think I'm sticking with the blue though, because I happen to like it very much.
But then have you had a chance to kind of work with other artists or cultural or aesthetic-wise in terms of the fabric or needing? There's lots of, but
on the fabric itself, no. I mean, in each one of the projects, there's some, well, the Knit Candela has Zahadid Code group in it, right? And then Soil is an architect is an architecture company, right? They work a lot with textures and materiality in that sense. But no, I got free will on the textile and the colors. I'll look for the people that could help me out with the aesthetics of it more.
Perfect. Thanks a lot, Mariana. Fantastic.
Thank you.